Alright guys, we want to talk today. I want to finish up talking about end behavior. Last class we didn't get through the whole PowerPoint, but we got through enough. I think to get you a start on your homework. No, not in class. We'll start your homework this evening.
You said get a start on it.
I mean, we have so much to cover and so little amount of time that homework in class is probably never going to happen. We've got end behavior stuff. Okay, end behavior. We talked about it yesterday. Kind of developed an applet here to kind of show you end behavior. Okay. And I guess before I get to that, let's actually go to this here. If you guys deal with your, I wanted to, we finished class yesterday kind of factoring something that looked like this to show you that the first term is really the term that has like the largest impact on everything. In regards to end behavior, if I look at this function right there, okay, that's kind of, it's not what we started with yesterday, but it doesn't really matter what you start with. The practice is to factor out the leading term out of every single one of these terms. Okay, so my leading term is 3x to the fourth. I factor that out. So basically, the way this is called maple. I had to get maple to do that. So it does that division. So you see 3x to the fourth divided by 3x to the fourth gives me that one. 4x cubed divided by 3x to the fourth simplifies it to that. Okay, and then I still want to keep that 3x to the fourth. So I didn't use the right kind of command here to do this, but I put it back in. I plugged it back in here, and that's what I really wanted. That's what we had yesterday when we factored out that leading term, right? When I factor it out, it can't just disappear. Okay, it has to stay there. So I think I put that back in here. But then what happened is I wanted to take and show you how when x gets really, really, really big, what term is dominating the function, okay, in regards to our y values. And your calculator probably isn't going to be able to do this. Your TI-83 or 84, obviously only has like a space for 10 or 9 digits when it feeds back something to you, so it's not going to be able to put this number back. If it does give you that number, it puts it back in scientific notation. You have to read that. But a lot of times when you start using x values that are really, really big, your calculator isn't going to have the ability to do it, and it'll just say overflow error. Okay, like if you take, earlier today we dealt with a million, and I think we had to raise a million to like power of 20 before it gave us an overflow error. Okay, but if I were to take not a million, but maybe 10 million or a billion or something like that, and plug it into x to the fourth, it'll probably instantly give me an overflow error. So your calculator has some limits in the size of numbers it can deal with. Maple though, it doesn't really have too many limits in regards to the size that it can computate. Okay, or not compute. That was a weird word I just made up. So when and A is what I'm showing. I'm calling this thing here when I plug in a million for that x, 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 and a million for that x. Okay, and it calculates that and it spits back this number right here. Okay, it's a pretty large y value, right? That's ultimately what we're saying. When x is a million, this is the y value you get back for that function. Okay, pretty large y value. But if I just look at plugging in a million to that thing right there, that's what this line here is saying. Okay, the y value I get back is this number. Okay, you see that those numbers, they have the same amount of places, right? It's the same place values. Okay, so they kind of they end at the same spot down here, right? Okay, they both start with 3. Okay, and then we have what 1, 2, 3, 4, 5 zeros before I see a number up here. And obviously they're all zeros down here. But you see then, the difference between these two numbers is that one, right? Okay. Now that is a huge number. That 4000003, that's a huge number, right? But it's minuscule. It's very, 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 very small in comparison to that number. Does that make sense? It's like if I'm a millionaire and somebody steals 15 bucks from me, is that a big deal? No. Okay. So the idea is that those additional components, the other terms, have no real bearing on my y value. They do affect it, but that effect is negligible to the entire y value. Does that make sense? So that's why we can just look at the leading term to tell us what the end behavior is going to look like, what the graph is going to do in the long run. Okay. If we look at this, kind of gives you a visual of some functions here and how we can relate them. Okay, so I want to start with like a cubic function. Okay, so much x to the third power. Okay, we talked about this yesterday, I think. As x goes to infinity, okay, and this applet just kind of shows you, it'll trace out your x values are going to infinity, so you can see this curve. X is going to infinity, x is going to infinity, it's getting bigger and bigger and bigger and bigger. What's y doing? Getting bigger and bigger and bigger, right? And it's going to keep going on forever in that direction. So, what we end up with there is that as x goes to infinity, so does y. Okay? And then we can do the same thing with negative infinity. Okay? As x goes further and further this direction, you see that your y values are plummeting towards negative infinity, right? Okay. Now let's do another function. Let's say I have x cubed. Multiply that by, let's go 0.3 x cubed plus 2x squared minus 2x plus 8. Okay. Now the graph is going to look a little bit different, right? Okay, when I had x cubed, it didn't have these maximums and minimums. Okay, when I have additional terms here, those additional terms are what's kind of creating these ups and downs here, right? Okay. However, as x gets really, really big, okay, as my x values go this way, okay, look at the purple one. As my x values go this way, where are the purple y values going to end up going? As x goes to infinity, the purple y values go to infinity. As x goes to negative infinity, the y values go to negative infinity. Okay? So, was this function's end behavior the same thing as x cubed's end behavior? Yeah. Okay? And if I do, something like, I don't know, that graph, see what that looks like. Okay? It's a different graph now, right? Stop. Where's my stop there? It's a different graph, but is the end behavior the same? Mm-hmm. Yeah. And the end behavior is dictated simply by that thing right there. Okay? So if we understand what x cubed looks like, and its end behavior looks like, we should know what x cubed with any coefficient out front looks like, and any additional terms that we want to add on to the end of it. Okay? Now here's a question. What if I put a negative out here? What's a negative do to a graph out in front?
Flips it to the x-axis.
Flips it over the x-axis. So, what's going to happen to the end behavior? They flip-flop, don't they?
The opposite.
Now as x goes to positive infinity, y is going to negative infinity, right? And as x goes to negative infinity, y is going to positive infinity. Okay? I'm going to show you a chart here in a moment that kind of illustrates all of our end behavior relationships regardless of the type of function that we deal with. But I think it's kind of silly to memorize that chart. Okay? I want you guys to build relationships in mathematics and understand your math through relationships and not memorization. Okay? Because a chart is going to have 16 things to memorize. Okay? And you try to do that, you get to a test, or you're going to probably maybe transpose something, mess something up, try to memorize that stuff. Okay? But if you can build relationships and say, okay, I'm going to learn what x cubed looks like. Now I want to understand its end behavior. And then I understand transformations and what a negative out front does. And now I know how that impacts the end behavior of x cubed. Does that make sense? Okay? And then the hope is that you have another relationship that says, okay, if it's x cubed, that's what it looks like. That's what the end behavior does. But if x to the fifth, does it look kind of the same?
Yes.
Yeah. It just goes to infinity a little bit faster. Okay? If we were to put x cubed and x to the fifth on top of one another, x to the fifth is going to be kind of tighter to the y-axis because our y values are going to be much bigger, much faster. Okay? Now we could change that x to the fifth. I'm going to put in quite a few terms here because end behavior-wise, x to the fifth is just like x cubed. But if I put some extra terms in here, the behavior around 0, 0 is not the same. Okay? Now, when I say the behavior around 0, 0, that's kind of a vague statement. Okay? Close to 0, 0 could be like between 10 and negative 10. Could be, negative 5 to positive 5. Could be negative 100 to 100. Could be negative 1 billion to 1 billion. When I say close to 0, because we're in respect to infinity. Does that make sense? Billion is a very tiny number in respect to infinity. Okay? So when I'm talking about what the graph does everywhere except for its end behavior, that stuff kind of changes depending on these additional terms. So if I look at that graph, it looks like that. Okay? We have some more ups and downs, right? Okay? But look at what happens as x goes to positive infinity. As x goes to positive infinity, get rid of this one. X goes over here to positive infinity. I'm going to have to move my, I'm going to make this a little longer. Drop these. Maximum 15. Speed up a little bit. Wow, that was a little fast. Alright, so if I look at x values going to positive infinity, where does the y value shoot off to? Positive infinity, right? And if I look the other way, if I do the x values going to negative infinity, the y values again shoot off towards negative infinity, right? Okay? So the idea here is even though the behavior of the graph around 0, 0, okay, where we've got those maximums and minimums occurring, even though we have that stuff, it doesn't impact the end behavior, okay? So every x to the fifth might look something like that. It might look more like a cubic or whatever, but end behavior is going to be exactly the same as x to the third. Does that make sense? What do you think the end behavior of x to the seventh is going to look like?
The same thing.
The exact same thing. Okay? So if I put a seventh power there, okay? Now we see that it cleaned the graph up around 0, 0, right? Okay, we don't have all those peaks and valleys anymore, but if I look at x getting bigger in the positive direction, the y value goes to infinity again. As x goes bigger and bigger in the negative direction, y goes to negative infinity. Does that make sense to everyone? Okay? So you recognize, the hope is you recognize, I don't really care what the power is. I just care that the power is odd. Okay? Because all odd degrees, leading degrees, are going to show the same behavior. Okay? Now, we haven't talked about ones that were even, right? The first even function that we deal with is x squared, right? Okay? Well, as x goes to positive infinity, x moves here, the purple y values are going to positive infinity, right? And as x goes to negative infinity, the red y values are going to positive infinity, right? Okay? However, if I start changing that, obviously we know this stuff. We can move this thing around. Yeah, kind of zoom in here. We can move the graph around. That graph looks a little bit different than what we started with, right? But is the end behavior still the same? Yeah. So the plus x and the minus 6 really didn't have any effect on the y values in the long run. Okay. Let's talk about something to the fourth. If I put a fourth power there, okay, it's no longer that parabola. The red one's still the parabola, right? Okay, but now, okay, is the end behavior still the same? Yeah. Okay, so it just happens a little bit quicker. I get to positive infinity a little bit quicker. My y values on x to the fourth. Now here's some things that we can do. Let's say I want to, x to the third. Put a 0.2 in there. Plus maybe 3x squared plus x. See what that looks like. Okay. Does that look really anything different? Overall, no. Okay. So these additional terms didn't affect the end behavior. Let's go to a 6th power one. I'm going to put in point. It's going to be a long one, so give me a second. 6 plus x to the 5th minus 6x to the 4th. X cubed 9x squared minus 0.1x plus 5. So it looks a little bit weirder there around 0, 0, right? Okay? But look as x gets beyond, like looks like 2.5 maybe there. Okay, look as x gets over here, it's around 3. As x goes to the right of 3, y is going where? Positive 3. So as x gets larger and larger, if I plug in like a number like 40, y is going to be very, very large. If I plug in 45, y is going to be even larger than that. Okay? So I'm seeing that as x goes to a bigger number, as x goes to infinity, y goes to infinity. Okay? As x goes to negative infinity, y is going to positive infinity again, right? So we see then that x squared, x to the 4th, x to the 6th, they all have the same behavior, right? In regards to end behavior. Okay? So then I can kind of interpret that x to the 12th, x to the 18th. They're all going to be kind of the same, right? Now, all this stuff that's happening on the inside around 0, 0, that stuff is directly related to that jump. Okay? And that's what we're going to talk about later in this course, is how do we find those maximums and minimums that are occurring inside that function, and talk about the zeros of that function. Okay? And that'll happen here in the next couple of days. And also you'll get to a point in calculus where what we learned this year and what we do this year, you will have much easier techniques in calculus to find. Say I want to find this point right here, or that point right there, or these 2 points there, or that point there. Those are all local maximums and minimums, right? When you learn about derivatives next year, okay, you'll do, and it's really easy to find the derivative of a polynomial function. You'll work with finding then those maximums and minimums using the derivative of that function. Okay, which if you can multiply, you can find that derivative pretty easily. So in behavior, what we've got here, we've got a couple of rules that I want you guys to. I don't want you to memorize them. Okay, but I want to kind of discuss them real quick with you. Kind of rephrasing everything we've already said. Okay? It says P has odd degree. Okay, so if your polynomial is x to the 3rd, x to the 5th, x to the 7th, x to the 9th, whatever, if it has an odd degree, it's going to look like these two things. Okay? What I remember, and the dotted lines here are just telling us that stuff in around 0, 0, however many times it goes up and down, we don't really care. Okay? How many maximums and minimums you have, that type of stuff, we don't care. We're interested in behavior. If I have like x to the 3rd, we knew that that end behavior looked just like that, right? So what I do, I don't remember this. I don't want you to remember this chart. I don't want you to memorize it and be able to reproduce it verbatim, word for word, like this chart is. I want you to remember that x cubed, what its end behavior looks like, what that function looks like. And then make the relationship that, well, x to the 5th, x to the 7th, x to the 9th, all kind of have the same thing, right? They all do the same thing, okay? And then you can determine, well, if I know what x to the 3rd looks like graphically, and I can determine, x to the 3rd, when I go that direction on the x-axis, the y value is going that direction, I should be able to come up with that statement about approaching infinity in the x direction and the y direction, okay? And I should be able to come up with one with x going to the negative infinity, okay? Then people say, well, now I've got to memorize this second chart because that's when the a value is a negative now. Okay, over here the a value is positive, right? So it's positive x cubed. Okay, I would not memorize this chart at all. Okay, I would memorize, or not memorize, but hopefully understand the relationship about what transformations do to functions. Okay, so if I had positive ax cubed here, and this is negative ax cubed, what does multiplying an entire function out front by a negative do? Reflects it over the x-axis. So when it reflects it over the x-axis, okay, the end behaviors also get flipped over the x-axis, right? Okay, so understanding transformations and understanding what x cubed looks like, hopefully, takes care of those two pictures, and ultimately ends up taking care of an infinite number of polynomials that you now know the end behavior for. Okay, because it doesn't have to be just x cubed. It could be x to the 5th, could be x to the 7th, could be x to the 9th, whatever. Okay, so that's that part of this chart with odd degree polynomials. Now we've got even degree polynomials. Okay? Well, I'm going to think about, in my mind, the simplest even degree polynomial. And that's x squared, right? And if a is a positive number, it should be concave up. Okay? Now the dotted lines again, I don't care what that looks like. Okay? Obviously in a parabola, we know that those dotted lines are parabolic. They should come down to kind of a minimum, one minimum. Okay? But if it's to the fourth or to the sixth or to the eighth or whatever, we got additional terms, it might have more peaks and valleys, more maximums and minimums. But we don't care. Okay? I know what x squared's in behavior looks like. Okay? I can determine that real quick. So then anything x to the fourth, x to the sixth, x to the eighth, x to the 10th has the same thing. Okay? And again, then, transformation-wise, if I make my a negative over here, how does that change x squared? Reflects over the x-axis, and now the end behaviors are also flipped over the x-axis. That kind of makes sense? Okay? So that's what I want you to think about throughout everything we do mathematically. Don't try to memorize things. You're gonna mess things up. You guys remember back to conic sections last year?
Yes.
When you had all these different rules for parabolas and hyperbolas and what are the other ones? Circles and ellipses, and you had to come up with like the foci and the asymptotes and that kind of stuff. And there was always a specific rule for finding all those values, right?
Yes.
And you mess those up a lot, right? Okay, because really it's just a sign change every once in a while in certain formulas that help you find the foci and the maybe the major and minor axes and stuff like that. If you were to build relationships in doing that and recognizing conic sections, you would never make those mistakes. And we're actually going to do that. That's the last chapter of this course is to work with conic sections. And I'm not going to ask you to memorize anything. I'm going to ask you to understand stuff. Does that make sense? And it'll make that process of conic sections so much easier than trying to memorize formulas and regurgitate formulas to come up with something. Okay? And that's what I want you guys to realize throughout mathematics. Memorization is going to fail you. Okay? Develop an understanding of what is going on. I had a conversation the other day with a student. They were worried about doing the calculation. They kept getting calculations wrong. And then I asked them, okay, well, explain to me what you're doing. And they couldn't explain to me the geometry. They couldn't explain why they were doing what they were doing. Well, that's the kind of the first hurdle you got to get across before you can even worry about the calculations. Okay? You have to understand what you're doing before you start going through the calculations, right? Okay, so calculations don't matter until we understand the procedures, understand the relationships. This one here, okay, it's just a quick example of the type of question you might see on a quiz. Keep doing that. On a quiz or on the test for this chapter, they'll give you that polynomial up there and they'll say, okay, can you tell us the end behavior? Okay? So I'm going to look at this. This is kind of the process I think I want you guys to go through. When I say end behavior, I know focus on that first term. Okay? Now it's even, so when it's even, I'm thinking that type of thing right there, right? Because that's kind of the end behavior of something x squared, right? Okay, so that's going to be the same for x to the fourth, x to the sixth, x to the eighth, all that kind of stuff. But now, there's a reflection occurring, right? There's a transformation. So my final answer is actually that end behavior, correct? So when you're doing these, I hope you kind of burn an image in your mind of kind of that picture, okay? And now I can say, well, so when they ask what the end behavior is, they're going to say, as x goes to infinity, where's y going here? Negative infinity. As x goes to negative infinity, where's y going?
Negative infinity.
Negative infinity. Okay? Just be careful in how they word stuff, because sometimes they'll say, even if you look at that chart in the last slide, they said y goes to negative infinity as x goes to infinity. I think that's kind of backwards thinking. Okay? I like to think about what is the x doing, and then from those x values, what's y doing? Okay? Because I like to look at the independent variable x first, and then look at the dependent variable off of that x. Okay? If you look at the chart in the last slide, it's kind of backwards. What if I gave you something that looked like this? And I asked you, Okay, what is the end behavior? What is the leading term there?
15x cubed.
Say it again.
15x cubed.
Good. Okay, the leading term, remember, has to be the one of the largest exponent, right? And it's positive 15x cubed. That's something that WebAssign will do. In the past, I've seen tests do that, okay? Because they get you thinking, I gotta look at the first term, gotta look at the first term, gotta look at the first term. We only look at the first term when they're in descending order, right? So you would want to rewrite that as positive 15x cubed minus x squared minus x. Get used to doing things, writing your polynomials in descending order, because later, next week, we're going to start factoring an x to the third, an x to the fourth, an x to the fifth, and it has to be in descending order to do that. Okay? So good. So that end behavior is going to, if it's positive 15x cubed, okay, x cubed kind of looks like that, right? Well, 15x cubed and the minus x squared minus x is still going to, in the long run, this portion and that portion are going to look the same. So this one says, as x goes to infinity, so does y. And this one says, as x goes to negative infinity, so does y. Okay? So hopefully that becomes something that eventually, maybe middle of next week, end of next week, you instantly think about the first thing you see when you look at a function is the end behavior. Okay? It's going to be very, very important for us to be able to do. Do we have questions on anything as of now? We doing all right with this? It's pretty easy, Zach? Yeah.
I just have a question. I want to make sure that I'm like understanding this right. So basically, if I'm like, so say I'm moving x negative, I'm just watching negative, the y go negative. If I'm going positive, I'm just watching the y go positive.
Yep. Yep.
Okay, I just want to make sure I was understanding.
It almost seems too easy, right?
Yeah. I was
Okay.
confused.
And that's, I want to talk about it, and you might be thinking, like, you're beating a dead horse here, you're talking about the same thing over and over and over again. In the past, in the last 2, 3, 4 years, I get people to really botch end behavior. Okay, so I want to make sure that we do have a solid understanding of it. We're going to use zeros to graph. Okay, when we graph something, the end behavior and everything we're doing so far, the overall goal is for us to be able to create what we call a comprehensive graph. Okay, a graph that we know, here's what it does in the long run. That's the end behavior. Here's what it does around 0 to 0. Here are the x-intercepts. Here are the maximums and the minimums, that kind of stuff. Okay? So we want a comprehensive, good graph for any polynomial. So the first thing we really want to look at outside of end behavior is the zeros of the polynomial. Okay? It says if p is a polynomial function, then c is called a zero of p if p of c equals 0. Okay? Now that might be kind of weird, but that's the algebraic definition of ultimately an x-intercept. Okay? If I say, let's say I take a function p of x and I write that as, let's just say it's x squared minus 5x plus 6. Okay? Hopefully you know what that factor is to, like x minus 2, x minus 3, right? So my zeros are 2 and 3. Okay? What this means is that they're saying p of 2. Okay, if my zeros are 2 and 3, okay, if I choose p of 2, that means 2 squared minus 5 times 2 plus 6 should equal 0. Does that make sense? Okay. 4 minus 10 is negative 6 plus 6 gives me 0, right? Well, this thing here, this 2, is that 0. And a lot of times they refer to zeros as just some arbitrary c value. So what we're saying there is that p of c, in this case the specific c value of 2, okay, is equal to 0. And that tells us basically that was a 0 and that is a 0. Does that make sense? So the c values are, it's kind of weird, but c values are arbitrary x values. But they're calling them c so that you know that they're special x values. Does that make sense? Okay. So that's what a 0 tells us. But a 0 for the polynomial, a 0 for the polynomial gives us a y value back of 0. Graphically, geometrically, that's an x-intercept. Does that make sense? Okay. So a lot of times you might hear me say a 0, find the zeros or find the x-intercepts. We're meaning the same thing. And if we look down here, they're saying if p is a polynomial and c is a real number, then the following statements are equivalent. Okay? Saying c is a 0 of p or c is an x-intercept of the graph of p, those are equivalent statements. Okay? You might hear me say a 0 and x-intercept are synonyms. Okay? Mathematically, the 0 is for the polynomial and the x-intercept is for the graph. So are they synonyms? I don't know. I don't know if that would be accurate, but we can think of them that way. Because they'll never get you a wrong answer or incorrect thought by thinking that they're synonyms. Here it says x equals c is a solution of the equation p of x equals 0. Well, that's what we found out. If 2 is equal to c, plug 2 in, okay, I should get a solution to the equation p of c is equal to 0, or p of x is equal to 0. Okay? The third statement there says x minus c is a factor of p of x. Well, hopefully that is something that makes sense to us. If I have p of x was x squared minus 5x plus 6, the way I got 2 and 3 is I did this, right? X minus 2, x minus 3, p of x. And then we went x minus 2 is equal to 0, x minus 3 is equal to 0, and now we got x equals 2 and x equals 3. So that gave us our zeros, okay? But those zeros came from those things right there, right? X minus 2 and x minus 3. So if we call these our c values, then this is x minus c, isn't it? And that's x minus c. And these are two things that are being multiplied together. So when you multiply two things together to get a product, those two things are called factors, right? Okay? So this, x minus 2, is a factor of that, and x minus 3 is a factor of that. And if 2 and 3 are referred to as c values, then x minus c is a factor when x equals c is a 0. Is that okay? The reason we need to know that is that eventually they're going to say, okay, here are your zeros of your function. They're going to tell you that you have some function where your zeros are 5 and 1. What polynomial did they come from? Well, if this is c, okay, c is 5, then we'll go x minus c, so x minus 5. That's the factor, right? Then if this c value is 1, we'll go x minus 1. There's my polynomial. And if I wanted to expand that, could I FOIL that? Okay? So when they tell you the polynomial, you should have the tools to find the zeros, and that's what the rest of the chapter is really about, is finding those tools to factor x to the third, x to the fourth, x to the fifth type functions. But also, if we start with the zeros, we should be able to work our way backwards and find the polynomial that they came from. Okay? But all those statements are the same, so you might hear me say x-intercept or 0. Another one that we talk about is that is the same idea as roots. Okay? 0, x-intercept, root. You want to view them all the same. Okay? This is just an example. I would maybe suggest that you look at that on your own. It's just exactly what we just did, but with a different function. And I walk through the factors and the zeros and that kind of stuff. Something that's important for us to understand is what we call the intermediate value theorem. And we've actually used this, and I've talked about this in this class before, but it was when we used our calculator. Okay? Our calculator has the ability to find our zeros for us, right? Okay? And eventually we'll actually kind of use that to cheat a little bit. But if you remember our calculator, we went to our graph, and maybe I graphed something that kind of looked like that. Okay? And let's say that my interest was to find all of these zeros. Okay? Let's say that I want to find maybe this zero right there. Okay? If you remember going to our calculator, we had there's a function on the calculator that allows you to find the zeros, called zeros. Just going to find a red mark. But what happens is that when you get to that function on the calculator, it says, find a left bound. Okay? Well, left bound means just go, put your cursor somewhere to the left of that point on your curve. So maybe I put my cursor right there, right? Okay? And my calculator is going to, when I hit enter, my calculator is going to record that y value. Okay? So let's just call that some p of a, where that's a. Does that kind of make sense? Okay, x value there was a. Then it says, okay, find a right bound. So then I move my cursor to where I think the right-hand side of that x-intercept would be, and it's going to find that y value. Well, that's a different y value, so let's call that p of b, where b would be that x value. Okay? What is the sign of that y value going to be? Is that positive or negative?
Positive.
Positive. What's the sign of that y value going to be?
Negative.
Negative. Okay, so if my calculator, what the intermediate value theorem says, is if you have p of a and it's positive, and then you have some other p of b that is negative, that means that in between those a and b values on the x-axis, there exists a what? An x-intercept. You had to cross a 0, right? You had to cross the y value being 0. And likewise, we could have started with a negative and then transferred to a positive. Okay? So, that's the intermediate value theorem. It says if there's a sign change between the y values of two x values that you're interested in, or they're saying two c values, okay, then, or not two c values, yeah, two x values, let's call them a and b, then there is some c value here where p of c is equal to 0. So where the y value of that x coordinate, which we're calling c, its y value is 0. Okay, and that's the intermediate value theorem. Now, what I want you to understand is that if I don't see a sign change, that does not guarantee that there was not a a 0. Okay, so when I have this phrase here, this is an if-then statement, right? Okay, the inverse of it is not true. Okay, if you guys remember back to geometry, we talked about inverses, converses, contrapositives. Okay, maybe some of those phrases have maybe stuck with you, whether you know what they say or what they are. That might be a different story. But if we take an if-then statement and we put a negation on the front part, okay, so we say if p is a polynomial function with p of a and p of b do not have opposite signs, then there exists no value c between a and b for which p of c equals 0. That new statement is not true. Does that make sense? Okay? And this is the reason. If that's my function, okay, and let's say that I want to look at an a value right there, and I want to look at a b value right there, right? Well, here's p of a, here's p of b. What's the sign of both those? Yeah, they're positive. So there was no sign change. So can I make the argument with this graph that there are no zeros between a and b? No, there's two zeros between a and b, right? Okay, so you cannot negate that statement and still gain the same information, okay? Or the information that you're trying to get, all right? So the sign change tells you that there is a 0, but the lack of a sign change tells you nothing, okay? And that's something to think about mathematically all the time, is that when they provide me an if-then statement, that is the only way that I want to interpret that if-then statement. Okay? You've heard me say this before, but I think one of the hardest things about math, especially when you're learning on your own, is to be able to read and interpret what are they telling you, what are they meaning with the notation, with the style of writing, with if-then statements, that kind of stuff. Okay? So I want to make sure we do talk about some of that stuff periodically. When we do a comprehensive graph, okay, we're going to be looking for essentially these four things, and a little bit some extra things as well, I guess. What time we get out of here? 9:00. 56. Okay. So when we want to graph something, the first thing we're going to do is we're going to try to factor it. Okay? Because when we factor it, that's going to directly lead to zeros, right? Okay? So if I give you like a 5th degree polynomial or a 7th degree polynomial, you guys don't know how to factor those yet, right? Okay? Maybe the highest polynomial that you know how to factor is x cubed. but you probably only know how to factor that if it looks something like this. Okay, let's say that I put like I don't know, a 5 here and a 6 there. We only know how to factor that because we can do a greatest common factor and get back x squared plus 5x plus 6, and now it's broken that down to a quadratic that we can factor, right? Okay. So those are probably, right now it's probably our limit. Maybe x to the 4th if we see something factored by grouping we could do, but x to the 5th, x to the 6th, x to the 7th, we maybe don't know how to factor those yet. Now I know last year Mrs. Coles taught you synthetic division, right? Okay. We will use synthetic division to factor. That's why you learned it last year. Okay. So we'll learn something called the rational root theorem here in a couple days that will actually allow us to factor any polynomial that we come across. So regardless of how big the degree is, we should be able to find the zeros. So let's say that we factored something and we found zeros. Okay. So we found 3 zeros. The next thing says we're going to find test points. I think the next thing we should do is actually determine the end behavior. Okay? Because if this is x to the, let's just say it's x to the 5th. Okay? If I've got my zeros now, and if let's say it's a positive number out here, do I know that if there are no more zeros over here, then my graph is either going straight up or straight down, right? And it'll never turn and come back around because it has to cross the x-axis. So, if it's x to the 5th, end behavior of x to the 5th looks something like that, right? Okay? So now we have to deal with what we call our test points. Now my test points, I would want to find out some values, some x values between there, that tell me maybe what this graph does. Does this graph go up here like this and come back down? Okay? Does it bump here and then go back up through there? Okay? So we're going to find some test points in between those two values to figure out what the rest of the graph does. Okay? The hope is that you have the ability to look at the y-intercept as well. And if I have a y-intercept right there, there's a test value between those 2 points. So my graph has to go through there, then does that come through this point here and touch that? And then if it's got to bend back up to go through that x-intercept, right? So maybe it does something like that. Okay? So maybe my graph looks something like that. That's how we get a comprehensive graph. Now, us, right now, we will not have the ability to find out how low that goes without using test points. Okay? So, same thing here. We don't know how high that's going to go without using test points. Calculus, there will be a really quick technique to tell you what is that maximum and minimum value real easy. And that's why I talked about using derivatives earlier. But that's kind of the goal, is to kind of put everything together collectively. Maybe use a couple input values, test values, create an x and y chart, and to see what our graph is doing. Because the hope is later on, when you get to another course and you see a function in front of you, you have to do something additionally with that function, is to first have an idea of what it looks like. And then progress through whatever they're asking you to do with it. Okay? In the event of doing that, there's one more topic that we need to address, and we'll talk a lot more about this next week. But it's what we call multiplicity of zeros. Okay, so it's going to say shape of a graph near a zero. Shape of a graph near a zero. You guys remember hearing the phrase double root last year? Like if I have, let's say I have a function that just looks like f of x is equal to, like x squared, let's go, plus 4x plus 4, right? That's going to factor to x plus 2 and x plus 2, right? And that's going to give you 2 zeros of 2 and 2, right? Okay? So if we were to graph that, if we were to grab our calculators or whatever tool we're using to graph it, the graph here, I'm sorry, this should be -2. The graph is going to look at -2. There's my x-intercept. And we know it's a parabola, okay? So if it's a parabola, it starts going down. Eventually it's going to hit a minimum and go back up, right? Or hit a maximum and go back down. This is concave up. Okay, so my end behavior is going to look something like that, right? Okay? But now because I have this x-intercept, okay, if they were different numbers, that would mean I'd have to go below the x-axis and then come back up through somewhere else, right? Does that make sense? If I had an x-intercept of like -2 and +1, means I'd have to go through -2 and then come back up through +1. But because I have algebraically, two x-intercepts that are the same value, -2, that tells me I'm going to come down to that graph, that point, and I'm going to bump it, and then I'm going to be sent off in the direction that I came from, go back up. Okay? You guys remember seeing stuff like that? Okay? We would have called this last year, algebraically, that is a double root. Okay? Sometimes referred to as, instead of calling it a double root, we might say it has multiplicity of 2. Okay? And what all that tells us is that graphically, your curve is going to be what to the x-axis at -2? What's the word when we bump the x-axis or we just touch it once? Starts with a T, tangent. Okay? So, saying a double root tells us that my curve is tangent to the x-axis at that root. Okay? Now, the idea is, what happens if I have, let's say that I have, just kind of give you a picture of this real quick. It's kind of easier to do this way. Let's say I have a multiplicity of 4. So let's say, I'm just going to write it this way. Let's say I have x minus 2 raised to the 4th power. That's x minus 2 times x minus 2 times x minus 2 times x minus 2, right? What does it do to the x-axis here at 2? If I zoom in all the way at 2, it's going to do what to it? Comes down and bumps it, and it goes back up, right? So it was tangent, right? So that was a multiplicity of 4. What if I had a multiplicity of 6? What do you think it's going to do? Tangent. Okay? Now, the multiplicity, if it's even, it tells us that we are tangent at that spot. Okay? Well, what if I tried x? Let's just do x minus 2 to the 1st power. What do you do at 2? You go through it, right? You go from, we call these half planes, okay? If I look at my x and y axes, they take the two-dimensional plane and they cut it in half, right? That's what the x-axis does. So up here, quadrants 1 and 2 together are a half plane, and 3 and 4 are a half plane, right? So if I have a multiplicity of 1 for my 0, that means I pass through one half plane into the next. Let's say that my multiplicity was 3. What do you do there at 2? Do you pass through the half planes again? So what do you think happens if you have odd powers for multiplicity? You pass through. Even your tangent, odd, you pass through. So we'll finish up talking about that on Monday. There is a 3.2 assignment. It's not due Monday, but I would like you to look at it. Thank you, you too. Riveting stuff, huh?
Does he like take your